那欢迎大家来到我们 Lattice 课程的第4次。今天是由冰老师给大家讲 NTT。那我们就下面的时间交给冰老师。
好，等一下让我看一看这 OK OK 可以开始了对吗？OK 大家好，我稍微讲一讲，介绍一下 NTT 是怎么做的，但是我必须用英文讲，因为我中文有一点不可以，所以从现在开始我就用英文。但是如果有什么问题，可以用中文试一试问，然后尹飞也可以帮忙解答还是什么的。OK 呃 OK，现在就开始。So um so I'll be sharing about entities, and I first have some things to share. So I'm uh, I'm not a fan of talking about entities from the perspective of the butterfly. So usually when people share or do some sharings about entities, they first talk about the butterfly network. But I think this isn't a great way to understand entities, and I think we should understand them from how you get to this butterfly network and understand the reasoning behind why and how this works, rather than starting from this and then doing the bit reversals and talking about roots of unity from this network. So this sharing will be pretty much about that. And so number one, why entities, and number two, how they work. And I will mostly be sharing about them from my perspective, from how I learned them. So this talk will be slightly less theoretical because I'm an engineer at heart. So I kind of learned this thing through doing things, and reading papers is not my forte. So a lot of the slides I use here will be less formal and less strict with respect to the theory. And I will have sections in the presentation where I will stop and see if anyone has questions. So if you have any questions, please feel free to ask, either just by speaking out or typing in the chat when I pause in between the slides. So let's begin. So I think the first thing I want to clear up first is our entities equals to FFTs. And you can somewhat understand them as such, that they are equivalent, but entities are actually, application of fast Fourier transforms on finite fields, because fast Fourier transforms act on complex numbers. And most literature use them interchangeably, right? Because you see in popular stock literature and other papers, FFT and entity usually mean the same thing. So let's treat them as such here as well. And if you see them anywhere else in the future, you can also think of them as equivalent in the context of ZK, I guess. So part one, why do we need entities? Um, so a big computation that's required in lattice-based cryptography is polynomial multiplication. So this is from one of the papers where you see the paper saying that improving the efficiency of modular polynomial multiplication is critical to deployment of lattice-based PQCs. And also here in another paper, it says that operations account for about 30 to 50% of computation in lattice-based PQC and FE3. So something that we need to understand here are polynomial multiplications. So let's start with that. And we'll get to why this links to entity later on. So the simplest form of multiplication, I think we know, is just schoolbook multiplication, right? You have two polynomials, let's say, g equals to 1 plus 2x plus 3x squared plus 4x cubed multiplied by another polynomial. And if you do this the naive way, you get this result. But then the way you do this is very costly in computers because there's two big downsides to this. Because the result is of degree 2d minus 2, and the complexity is O(n) squared because you have to take every coefficient multiplied by every coefficient of the other polynomial. So this isn't really ideal for what we want. And just to go through this slide, which I roughly skipped over, formally, this is sort of known as a discrete linear convolution. And what this notation means is just that at the kth index, you're taking the gith index and then and the hk minus ith index summation over 0 to k. And that's how you get the results of y. But this essentially just means this. So yeah. So how do we fix these two issues, right? So let's first look into how we can deal with the issue of the degree. So that's where we introduce polynomial rings, right? We talked about polynomial rings a bit in the last session. So we simply take, after every polynomial operation, we modulo some polynomial phi. And the final polynomial's results would be at most as large as polynomial phi's degree. And in the context of lattice crypto, what we need is something like x to the n minus 1 or x to the n plus 1. And we'll touch more on why these two polynomials later on. Formally, this is known as a cyclic convolution. So you can see in the notation here that we quote unquote wrap around by some polynomial xn to the x to the n minus 1. So we can keep it bounded by a maximum degree n. Some notation to clarify here. So the term cyclic convolution refers to multiplication done over the ring zqx over z to x to the n minus 1. And for negacyclic convolution, it means modulo x to the n plus 1. But then in some other literature, they also use positive wrapped convolution and negative wrapped convolution. But they essentially sort of mean the same thing respectively. So it's up to you how you want to understand this better and how you prefer to see this. For me, I think positive and negative wrapped convolutions are a clearer way to understand the notation here. So the positively wrapped convolution, we use the ring over x to the n minus 1. And the definition is as such there on the slide itself. And conversely, we have negative wrapped convolution, which we do it over x to the n plus 1. And you can see the difference is just in the sign itself. So for the positive wrapped convolution, you get a plus, and for the negative wrapped convolution, you get a minus. So if we wrap it around,
Hello，
yeah,
可以到上一页吗？就是想再问一下，这里是在做 a 乘 b 等于 c 吗？
yes, for one, for the coefficient on the kth place. So you have like a c vector, and then ck is just on the kth position in the vector. Does that make sense? Hello.
也可以再给大家写的稍微的具体一点，然后给我们看一下吗？
Okay, sure. Let's see. Does this, how do I, okay. Let me try writing. Okay, so you can see this, right?
Yeah.
Okay, so C is like, it's just a vector. And then let's say you have like, sorry, I'm writing with mouse. So this would be like CK. And then you repeat this for all the indices.
嗯哼。
So this view is for if you view, sorry, if you view the polynomial as a vector in this form, right? And then you have uh, the same notation here. You have y with the kth index calculated this way uh, is a position in the vector.
嗯哼。
Does that make sense? Uh, okay, I guess I'll carry on. If anyone else has questions, you can also feel free to say. Yeah. So if we use cyclic convolutions, we sort of solve the problem of the polynomial result being of too big of a degree because we keep it bounded within uh, degree n in this case. But we still have another problem in that doing it this way, we still are sort of having this problem of O(n) squared complexity. But it turns out that under convolution theory, convolution in one domain equals pointwise multiplication in the other domain. So if you recall our above definition, convolution is just applying, let's see. Yeah, it's just doing this. So you're just doing multiplication normally. And what this means is that if you convert two polynomials in one domain into the other domain, you can just do pointwise multiplication. So we get something like the form below. So if you transform polynomials A and B into their entity forms, you can do pointwise multiplication. And then you can do the inverse transform to get back C, which is what you would have which is what you would have gotten if you just multiplied them plainly. But this time you have entities, which is n log n in complexity. There are also some other nice properties of entities. So one such property is that they preserve randomness. So if you randomly generate a random polynomial and then do the transform into the entity domain, this is equivalent to just generating the random polynomial in the already transformed domain itself. So you can sort of generate a random polynomial and just treat it as the entity form of, let's say, polynomial A. And the second nice thing about entities is that they preserve dimension and bit length. And this is important in that it can be stored where it was in memory. So sorry, there's a typo here. So it should be the result of entity can be stored where, okay, it's not a typo, sorry, where the polynomial A is in memory. So you can store it in the same place, is what this means. And you can also store the result for use in multiple computations to save CPU cycles. So maybe let's take a pause here. I think before I talk about entity and I inverse entity, are there any questions? I'll look in the chat a bit. So I'll repeat the question. So C here are basically the coefficient of x, A, x, B. Yes. So yeah. So CK here is the kth coefficient of AXB, A times B. Okay, let's carry on.
I have a question.
Yes.
我没有理解这个最后一句，the result can be stopped 啦，to save CPU cycles。
Oh, it just means that you don't have to transform it again. So you can transform it once, and then you can store it in memory and then reuse it again. As long as the result is still there. You don't write over where it was in memory.
是指我只要还要继续用 NTT 做运算，我就可以不用做 inverse，还是说前面那句，因为它们的长度一样，所以我 NTT 的 vector 也可以放在原来存放呃那个 R 那个，就是可以放在原来的那个位置，还是说我可以不用做 inverse？
So you still have to do inverse if you need to do it. It just means
嗯
that if you are doing transform on the polynomial more than once, you can just store the transformed polynomial once instead. So you don't have to transform it multiple times.
明白了，谢谢。
Okay. Let's now talk about entities themselves. So now that we have the motivation for using entities, let's talk about what they actually are. So the entity of a sequence is just each coefficient in the vector, or rather the polynomial coefficient, multiplied by some omega. And we'll talk a bit about what this omega is later on. But treat it as some variable for now. And you sum it over n minus 1. And the inverse entity is doing the same except with two differences. So now the omega is negative ij, and also you have to do it scaling by 1 over n. So n minus 1 here. Omega here would be the primitive nth root of unity in ZQ, if and only if omega n to the n is equivalent to 1 mod q. And then for all k less than n, you cannot have a omega to the k that is equivalent to 1 mod q. And here we have another, definition that we need to clear up here, right? Because what is a root of unity? A root of unity is any complex number that yields 1 when raised to some integer n. Otherwise, we can call it the nth root of unity. And these roots of unity form the roots of the cyclotomic polynomials which factorize polynomial x to the n minus 1. So you can sort of visualize this in a circle, because what I said here in the past two slides is sort of like a lot of notation, but intuitively you can just look at this circle to try to understand what roots of unity are and why they are used in entities. So imagine if you have 3 points, or like a degree 3 polynomial. If you equally space out the points in a circle, you get these 3 points on a circle. And the omega to the n of this circle would be 1. here. And then the top left point and the bottom left points respectively would be omega and omega square. And then of course the first point on the right would be omega to the 0, right? So here you would have 3 roots of unity. And then what you can do here is you can, if you need n roots of unity, you can extend this to, you can draw as many points as you want on this circle to get your roots of unity. So a simple example, right? Because, so there's a question in chat. Is ZQ supposed to be a prime field? Yeah, so I'm getting to this example now. So this is a simple example of how you can calculate roots of unity in a very small prime. So here you have a very simple q equals to 17, and then you get 2 as the primitive 8th root of unity, because you can see, and you can calculate this yourself as well. If you get 2, if you calculate 2 to the 4, you get -1, because that's 16, right? So so that's simply going back by 1 from 17. And then if you go 2 to the 8, you get 1. So if you visualize this on a circle, it's also sort of easier to see. Right. So we have sort of the ingredients now, right? Because we talked about convolutions, we talked about roots of unity, but what is the actual trick behind how NTT works? And this is where we talk about something called the FFT trick, which is here. So this is a slightly bigger slide, so let's go slowly over this. So the theorem is remain a theorem in ring form. So if you have R is where I can be decomposed into ideals in R from I1 to IK, you can sort of get a ring isomorphism where you have a map phi that maps Ri to all the intersections of the smaller rings. And what this means in practice for us is that we can also do the same thing with the rings that we talked about earlier. Because let's say if we have a polynomial x to the power of 2m minus omega squared, we can break this down into 2 parts. We can break this down into the left side where you have zq x to the m minus omega, and then the right side is you get a you get modular over x to the m plus omega instead. And practically this sort of maps to, you have a prime and a double prime, where a prime equals to a mod x to the m minus omega, and a double prime is equals to a mod x to the m plus omega. And if you think about this more deeply, if m is a very big number, you can apply it recursively all the way down to linear polynomials. So then you'd go back all the way down to constants polynomials. Visually, you can sort of understand them as such. So if you have x to the n minus 1, you can map it on the left and right side. On the left, you have x to the n over 2 minus 1, and on the right, you have x to the n over 2 plus 1. And you can do this recursively all the way until you get down to linear terms.
Hello，我可以问一下吗？就是
Yes.
啊我们为了就是这样，做 log n 的分解，所以我们要选这个 n 是一个 power of two，对吗？
Yes. So for this to work, n has to be a power of two. And I guess that's also why most practical implementations of FFT, they use powers of two, or they pad the coefficients to size power of two.
嗯，还有一个问题是，这个 x to 的，嗯，就是怎么说？就是看起来好像这个 x 二分之 n 次方加一是可以拆成下面两个，对吗？然后那意味着欧米伽 n 的四分之 n 次方，欧米伽 n 的二分之 n 次方是应该等于负一，对吗？
Sorry, come again. Which part are you talking about? The right side?
啊，对对对，是这里。就是为什么可以把这个 x 二分之 n 次方加一分解成下面这两个？
Okay. Let me see. Yeah, because
我知
if you
道，
recall, the uh, if we pick an omega to be equivalent to one, then if you have half of that, uh, you get minus one, right? Because you see like on this slide itself. So if you have eighth root of unity, the fourth two to the four here is equals to negative one. So you sort of have the same thing here. You can replace it with the roots of unity.
嗯，好的，那个评论区还有一个问题，
Okay, let me go one by one. So uh, Sven asks, what does the A prime mean there? So the A prime just means it's the transformed, or rather the new A. So it's just note. What is A exactly here with respect to A prime and A double prime? Intuitively, A not equals to A prime and A double prime, right? Yeah. So A is not equals to both of them. So it's just notation to see the distribution, I guess. 因为 omega 是它的 n 次根吧。Yeah, so that's the answer to the question. Why entity transform was not applied to NTRU? So I'll have a slide at the end that I think might answer this question. But yeah, there are some exceptions to the rule. So just now, Infe asked that if this can be applied to, if this can only be applied to powers of two. And the answer is yes. This trick would not work for something that's not a power of two. And there are some other tricks to do with that, but I don't think I will be covering them in this talk. But I'll briefly mention them below, and then I'll also share resources for how those tricks work. I'm mostly not covering them because I don't understand well enough to talk about them. Uh, W,
Sorry.
yeah, sorry, someone
Could
wanted to
you
say
zoom
something.
in the slide, please?
Oh, okay, sorry.
Thank you.
Is this better?
Yeah, much better. Thank you.
Yes, sorry about that. Okay. Muzi also answered the question just now. Yeah. So n over 2 is -1. Yeah, correct. Okay, any more discussion points to bring up for this? Otherwise, we can move on. Yeah, so to summarize this, we can do this splitting because of this very nice theorem, Chinese remainder theorem. And why we can split xn over 2 plus 1 in such a way is because if you think of it as a simple example, you can if you go halfway around the circle, right? Intuitively, you get -1. So whenever you have trouble visualizing, you can go back to this and try to work it out from this circle itself, because yeah. Okay, let's move on from this tree. Let's now talk about what this mapping means, because we've sort of understood how the isomorphism works. And practically how we would implement this is through the mapping below, where you have phi and phi inverse. So phi is the forward transform, it's the entity. And then phi inverse is the inverse entity. So you would have the ith coefficient, ai, xi, equals to this long notation on the right. And same for the inverse process, except the difference here is that you have remember earlier on when we talked about inverse entity, we needed to multiply by the inverse omega. So this is what we do at the bottom here. We have omega to the -1. And also we also have to do it, do the scaling. Before it was 1 over n, but this time we have 1 over 2 because we are sort of splitting by 2 each time. So I hope this also answers the questions earlier. So A prime and A double prime are just ways to notate the type of coefficient it is, whether it is in the base form or whether it is in the entity form. So A would be the base form, and then you have A prime and A double prime in the entity form. And of course, when you apply the inverse transform, you get back the base coefficients form. So something I wanted to bring up here is if we take a look at these two notations, right? And this is something we see here in the previous slide. If you have A prime, AI prime, right, equals to AI plus omega multiplied by AI plus M. And same for A double prime. This looks familiar to something that we might see in other places, right? And this is actually just the butterfly itself. So you get from the left side to right side without looking at the butterfly network that I showed in the front, in the beginning of the presentation. And that's kind of what I wanted to show with these with these slides above here. That's how we can get to the butterfly network without actually even drawing the network itself. So you would draw this as such, in many posts that you see, right? You have the butterfly network and then you get the result here. But you can come to the same conclusion of the butterfly network just by understanding the FFT trick that you see here. So by doing the splits with Chinese remainder theorem, you can get to the Cooley-Tukey butterfly. And same for the inverse FFT. This is the GS butterfly. And we can take a look a bit at the notation again. So if you have AI equals to A prime I plus A double prime I over 2, this is essentially on equation 11. This is let's see if I can draw here. So this is just this part here, right? And then the second butterfly is this right notation here, which you can see here. So they're equivalent. So just by breaking it down this way, you can get the butterflies themselves without having to draw the network. Are there any questions on this part? Okay, then this is pretty much the full picture with the entities. There are two types of butterflies here. You can apply so I'll explain the notation first. So on the left side, you have the forward transform, where you use the Cooley-Turkey butterfly, which is the butterfly presented here. So you have A plus omega B for big A, and then for big B, you have A minus omega small b. And the NO right arrow BO that you see at the bottom there, it just means natural order and bit reverse order. So what does bit reversal mean? And I'll explain this just by drawing some examples. So it's very, let's see. So let's say you have, so we have A1 here, right? So this is basically the first index. But if we reverse the bits, we get the 100, right? So this is just what it means by natural order to bit reverse order. So it's just the nature of this algorithm that when you calculate using Cooley-Turkey butterflies, you get the bit reverse output. So that's why you have, so that's why on the results here, in the middle here, you have like a scrambled coefficients, sort of. You have A0 and then A4 and then so on. But the nice thing about the second butterfly that we saw earlier on is that if you combine this with the GS butterfly, it actually accepts the bit reverse order input. So you can plug the output of the left side into the input of the right side. And then you get back the result in the right order. And there are other forms of butterflies, of course, you can use, other combinations. But if you do it this way, you can skip the whole bit reversal needed for computation. Because if you look at some implementations out there, they actually do implement the bit reversals because they're using different butterflies. Okay. Okay, yeah. So I think someone asked a question about NTRU, and I think this sort of has the answer, even though I can't really speak about it. So there's a rough table here of all the rings that are used and the methods and algorithms that we can use to do entities on them. What I want to point out here is most of them use what we've already covered. So the full NWC based entity. So that's what we covered. And that's the nice case where all of them are entity friendly. And by entity friendly, it just means that they are a power of 2. and they satisfy this congruency here. But in some cases, we have to use different tricks, right? So for example, if you see Saber, Saber has an entity unfriendly power of 2 Q. So then we have to use method based on large modulus, which I'll briefly speak about it, but I don't know it too well, so I don't want to say it too clearly. You choose a big N, which is bigger than Q. So N must be more than N squared to the N squared Q. And then you first do multiplication in that domain, and then you reduce it further. For details, I will link to the paper and then you can check it out. But this is roughly the big idea here. And then for NTRU and NTRU prime, there's also similar troubles because they don't use entity-friendly primes, N and Q. And you have to do some other tricks to sort of apply entity on them. But they're mostly based on similar tricks where you pick a difference N and then you apply entity on the bigger domain, and then you try to reduce them again. So, sorry. So I think, yeah, so I have these two references, but I think this is roughly where I want to stop for the sharing. Happy to take any questions or any points of discussion here.
感谢炳老师的分享，大家有什么问题可以语音或者是在这个聊天框里向炳老师提问。
Okay, there's a question in chat. So you're asking about bit reversal, right? Let me try to see if I understood the question. So if you do A1 to A8 in order, and then when you do NTT, it will come out in bit reverse order. Is that the question? Yeah, so it's will come out in bit reverse order, or rather the inverse order. So if you take the input as the bit reverse order, you would get output in the natural order. So there is, in one of the paper I linked below, there's a full map of all the types of butterflies. And you can tweak the butterflies to take either natural order or bit reverse order. So you can sort of mix and match algorithms. Does that answer your question? What is the complexity of using NTT in poly multiplication? Yeah, it's O n log n, because you're splitting the problem into two always. And then when you multiply, you just do pointwise multiplication. So you don't have to multiply all the coefficients one by one. Okay, the other question. Some rings are not x to the n minus 1, are not modulo x to the n minus 1. Can we still use NTT? Yeah, but we have to apply different tricks to those rings. So these are the methods on the right, but then I'm not too familiar with those methods, so I won't be fully explaining them.回到刚才 butterfly 那个 slide, okay. So this one, so entity simple. Yeah, yeah, exactly. So if you have A1 to A8 in order, you get the output. Let me draw it. Yeah, you get this output here, right? Sorry, yeah, this one. High level, can I say that we first convert a coefficient form polynomial into its corresponding point form polynomial, then multiply them, and finally convert the point form poly back to coefficient form? Yes. So that is exactly what we're doing. Here.对，柯老师，我在用你的导师的 paper。So I think just personal bias that I think these two papers are very good to understand entities. And maybe these two papers are all you need. I'll share the slides on the GitHub after. I realize I haven't uploaded it yet.
No.
大家还有什么问题吗？可以再问问丙老师，我们现在还有时间。然后没听懂的也可以让丙再给大家仔细的讲一讲。
Hi, Miss Bing. I have two questions. One, can you use FFT instead of an NTT? And how can computers omega?
How
Thank
to
you.
compute omega? Okay.
Yes.
So the first question was, can you use FFT instead of NTT? So you can treat them as sort of equivalent, even though I realize that some papers they use like FFTs or some implementation they use FFTs, right? And then they actually calculate the reals and complex. But then that depends on implementation details, I think. But typically, I would say entities are what you should go by, but they're more or less equivalent. You can sort of equivalently understand the same thing. And then the second question is, how do you calculate the root of unity, right? I don't think there is a efficient algorithm to calculate the root of unity, unless I'm wrong. So you almost always have to pick like a nice prime and then try to for this small one, you can brute force it, right? But then there are some other efficient algorithms to try to find roots of unity where you basically trial and error. Does that answer your question? What is the cost to convert the polynomial from non-entity form to entity form? Is it huge? So it's in terms of complexity, it's going to be n log n, as because you always split the problem into two, but then you do it for every term, so it's n log n. Relatively speaking, it's less than directly multiplying the two polynomials together. So it's always preferable to use entities to multiply two polynomials.
冰老师可以看一下聊天框的问题。
So is the question, let me try to understand this. So the question is, do you need to transform it multiple times? And am I understanding it correctly? Yeah, I don't fully understand the question.
应该是问是不是做计算的时候要先做 NTT，然后计算完再 INTT，然后 NTT 和 INTT 都转换都有 n log n 的计算开销，会不会很 costly？
Yeah, yeah. So if you want to take advantage of the point-wise multiplication, then yeah, you always have to do that. That's why for some smaller polynomials, you actually just do naive multiplication, and it's faster than converting. So there is a trade-off, I guess. But typically, you would work with very large polynomials anyway. So you would want to do this conversion, usually.
这个我可以稍微补充一点点，就是像在Kyber-DISM 这种方案里面，比如说一个加密或者是一个签名算法，会做比较多次的什么加法、乘法运算，然后有可能我们 sample 的那个 public key 它是一个random 的那个 matrix，这样的话就你 sample 的时候就是以 INTT 的形式去存，然后就是只在最后这些运算都完成之后再做一个 INTT，不会说是我每一次的计算都需要 NTT 加 INTT，就大概是这样子的，不知道可不可以回答你的问题。然后冰老师还有一个关于 roots of unity 的问题。
Why do we choose the root of unity? Because of decomposing x to the sum k plus 1. Yes. When you, if I understand this question correctly, you're asking why we need roots of unity, right? And essentially, yeah, we want to decompose that nicely. And if you go back to if you have trouble visualizing this, you can go back to the circle again, where you can see that, the roots are basically just points on the circle. So a very big polynomial and you find points on this circle that you can split the big polynomial into. So the points on this circle essentially is just the leaves on this tree. You can think of them as something like this.
OK，我们时间也差不多了，大家好像也问了挺多问题的，可以，下面再跟冰老师在群里面聊，或者是周六的时候再参加我们的答疑讨论。然后我们今天就感谢冰老师给我们介绍的 NTT 以及 NTT 的运算，然后就今天就这样吧，谢谢大家，
谢谢冰老师。
谢谢冰老师。
谢谢大家。